Good morning everyone. Welcome to our channel Engineering Phantom. So here we gonna design a 60 SRAM cell on Cadence Virtuoso tool. So we will do schematic of 60 SRAM cell here with sizing and then try to do the read and write operations of 60 SRAM cell. Let's start. So firstly we operate Cadence Virtuoso tool here. So let's go and open our design. Okay, so here I have placed transistors, 2 PMOS and 4 NMOS transistors. Like here the 2 PMOS transistor will work as a pull-up MOSFET, and the rest 4 NMOS, 2 will act as an access and 2 will act as a pull-down transistor. So we have placed all 6 transistors which we required. Let's move forward. So we zoomed it. As we can see, 2 PMOS, 2 NMOS. Let's align the PMOS with NMOS so we can do a inverter here, because 60 SRAM cell is basically nothing but two combination of two inverters connected bistably, directly connected with each other. We can say it bistable latch. Okay, so let's design a bistable latch using the two inverters. Here we align it both PMOS with NMOS. Okay, so alignment is done. Let's connect them to form an inverter. So firstly we will connect the drains of PMOS with drain of NMOS. Let me connect it. So this our first inverter is done. Drain connection is done. Then we connect source of PMOS, source of both PMOS for VDD connections. Before that, let me connect this body terminal with source terminal of MOSFET. So here for first PMOS it's done. For the NMOS one it's also done. Body terminal is connected with source terminal. So for second inverter as well, body terminal of NMOS is connected with source, and similarly body terminal of PMOS connected with source. So it is done. So let's do further process. Try to remove these words but unable to remove it, so let's ignore these words. Okay, so the connection is done. Both drains of inverter 2 are connected. So let's flip it to connect it properly and for our conveniency. Okay, we will use vertical flip. So flipping is done this way by flip icon as we seen. So let's move it little bit closer. Its distance is much more than required. So let's move it further to reduce the distance between the two inverters. So here we are trying to form a bistable latch. Okay, so this distance will be enough. Place it. So let's complete our bistable latch to complete SRAM cell design. So this is our gate of second inverter connected. Similarly, the gates of our first inverter will also connected with each other. Okay, so its kind of inverter structure is connected. So we are giving both the inverters common VDD. So this way both drains of PMOS were connected. Similarly, both sources of PMOS connected, both sources of NMOS will be connected for common ground connectivity. Let's move forward. So here, yeah, connection is missing. So now let's complete it. Okay, so now it's completed. Yeah, both source of NMOS were connected for common ground connectivity. So the two, so here we have completed our bistable latch. As we can see, inverter 1 and inverter 2 are completed for a bistable latch design. It's still not a bistable latch because the input of the first inverter is not connected to the output of second inverter, and our input of second inverter is not connected to the output of first inverter. So let's move forward. Firstly, we will settle the excess transistors. So we have to flip them because we need to connect the drain with the outputs of the inverters. Let's move it closer. Yeah, so it's done here. So similarly, let's move the second excess transistor closer. Yeah, it's done. Okay, so now it's at in simpler distance. So here the body terminal of these both access transistors are not connected with the sources because their sources will be connected with bit line and bit line bar. So but we required them to be connected at ground, so we'll not connect them body terminal with source. Let's see, move forward further. Okay, so let's take the pins. Here I am using in out pins because it's easy to give them input and output both at the same time, so I always use in out pins. If you prefer, you can use input pins for VDD and ground, and output pins for the terminals where you want to see the output, but I will request to use in input output pins. So let's set, so let me write one by one the names. So we need QA terminal, then a QA bar terminal which we call QAB, QA underscore B, QA bar. So we also required word line, then we required bit line and bit line bar. Yeah, bit line and bit line bar. Then we required ground. Okay, so let's put the pins one by one. So first of all we written QA, so put the QA pin, then QAB pin which is inverted form of QA. So we placed two pins. Now word line pin, we place word line pin here. Okay, yeah, this will be good place. Let's place it. Next is bit line, so this is our bit line will be placed here, and next is bit line bar. Okay, so next is ground pin is placed, and here we are still missing one pin which is VDD. So again we create pins, name the pin VDD and placed it. We are placing it here, so all pins are placed. So let's give wire connection and complete the pins, complete the SRAM design. So yeah, we press W to get wire it is little too much. Let undo it and try again. Oh yeah, here is undo option. Here we can undo it. Let's try again. Press W and try to connect it. Okay, it's again wire size is too much. We again undo it, and this time we will use the wire option from this box. So let's try this time. Maybe this one will be good, correct one. Yeah, it's looking fine. So let's connect the other pins. So let's connect the word line pin with the gates of access transistor. Okay, the other gate is also connected. So word line connection done. Let's move further. So bit line bar is connected with the other access transistor, and let's move to the bit line which is connected to the respective access transistor. Okay, so let's connect QA with output of inverter 1. So this will be our inverter 1 and this will be inverter 2. So let's connect QA bar at output of inverter 2. Let's connect the access transistors at the output of each inverter. Before that, output of inverter 2 is connected with inverter 1 input, and output of inverter 2 is connected at input of inverter 2. So both were connected. So this is our cross coupled latch, bistable latch. Inverter 1, the input is connected to the output of other inverter. Similarly, the input of this inverter is connected to the output of other inverter. So this is called bistable latch. Okay, so let's move forward. We connect access transistor at the output of both inverters. Second access transistor at the output of other inverter. Connect ground. Okay, so here we have one thing, the body terminals of access transistor are still not connected. Let's connect them. Okay, yeah, other body terminal is also connected with ground. So this way we have completed our 60 SRAM cell schematic. Okay, it's looking complete. Yeah, so now come to the sizing. So sizing, there are two things, pull up ratio and pull down ratio, or bit cell ratio we can call it. So firstly we are going with pull up ratio, which is basically access transistor with divided by width of pull up transistor. So and one thing is, the sizing is pull up transistor have the smallest width, then access transistor have just larger than pull up, and NMOS has the largest width, which is larger than access transistor. Similarly for the other part of the inverter. Okay, so let we keep the width of pull up transistor 120 as it is. Okay, so both the pull up transistors width will stay as a 120 nanometer. Similarly this one also 120 nanometer. So to maintain the pull up ratio, here the access transistor should be 1.5 times of PMOS. So we will get approx 0.75 as a pull up ratio, which is a width of access transistor divided by width of PMOS transistor. So width of PMOS transistor, so yeah, width of access transistor divided by width of PMOS transistor, which is 120, equal to 0.75. So 0.75 into 120, or we can say just make it 180. So divide by 180 divided by 120, we will get 0.75. So let's write it. So 120 nanometer width, we have, sorry, 180, it will be 180 nanometer for this access transistor. Let's press it, remove the 2 and write 8. So this way we have settled 180 nanometer width for this access transistor, and similar manner we will set it for the other access transistor. It will also be 180 nanometer. Okay, so access transistor sizing is done. So let's move to the last sizing of pull down transistor. So the pull down ratio should be 1.5 times, which is NMOS, width of NMOS divided by access transistor. So access transistor is given, which is 180. 180 into 1.5 times, so it should be 270. So let's set it 270 nanometer. If we don't follow the standard sizing rules, then our SRAM will not operate properly. Maybe read or write operation will face some issue. That's why we have to keep focusing on this sizing while designing SRAM cell. Let's set the sizings of both NMOS or pull down transistor to 270 nanometer. Okay, remove the one. So yeah, it's 270 nanometer set. So let's set the similar sizing for other pull down or NMOS transistor. It's also 270 nanometer. Okay, the width is set. So this way we have let's apply it. Yeah, so the sizing is done. Yeah, here is one mistake done by me. This source terminal of this NMOS should not be connected at this input terminal. It will be connected at this output terminal only. So you can rectify it by yourself like this. Here it's connected output, so it will also be connected at output. Thank you for listening. In next video we will see how the read and write operation were done on this 6